I'll share with you today a small corner, a ramification which has to do with operator theory from statistical investigation of separating outliers from the big cloud, the big bulk in point distributions. This is an eternal question and is related to spectral analysis, as you will see. And what I want to do in my talk, the first part, I'll recall and show you a few aspects of basic tool, which is a reproducing kernel bearing the name of Christopher and Darboux. And then I'll show you what challenges we face when we expand these ideas to 2D. Now, 2D is interesting because of image processing, of other point distributions, let's say on spheres, on tori. And you may ask why exactly 2D. You will see in a second, because two real variables form a complex one, and we'll exploit very intensively the complex numbers here. So the main question, here is a plot. It's just a graphic plot, nothing social, nothing political. We have a cluster of points, and there are, of course, outliers. And the basic question, which is of interest even more today than in the past, how do we separate the dense part from the outliers? There are many methods. I do not compete here with all statistical investigations. They are spanning over a century. But what I want to show is how this relates to objects we praise and we understand, namely structure of measures. And I will stand from a very ideal point of view, which is purely theoretical, and I'll consider simply a positive measure behind this plot distribution, and trying to separate, of course, a la Lebesgue, point masses from absolute continuous part, from singular part possible. So there are many methods here, as I mentioned. In general, potential theory helps. You put some masses here, you take a potential, the level lines will encircle these points, and if you study well and you are able numerically to do it, you will be able to detect outliers. I'll give some references at the end. So for our rather narrow and theoretical point of view, what we do is the following. 1D first. Lebesgue decomposition. We start with a positive measure on the line or on the circle, and there is a magic object, which I'll describe in a minute, which has the following quite remarkable property. The limit of it detects, whenever they exist, of course, point masses. And the weighted limit of this in an average, so almost everywhere, now we let X run over the interval, detects the absolute continuous part of the measure. This turned out to be very effective. I think Wiener already knew this and utilized it in signal processing, and more recently it entered into the mainstream of spectral analysis of self-adjoint or unitary operators. So what it is about? What is this magic object which you are talking about? We start with a measure. I'll consider from the beginning to be in the complex plane, rapidly decreasing positive so that polynomials are integrable. And we can speak without ambiguity of the orthogonal polynomial. I'll exclude finitely point masses. So as I mentioned, we go on the ideal part of the story, and we can speak about orthogonal polynomials of any degree. And this is already one, how to say, noble, aristocratic way to put the observable data in action. Namely, as you well know, orthogonal polynomials are interchangeable with the moments. I consider the moments of this matrix observables. And the question is, how much information do they contain? And quite a lot, as you well know. I'll remind you a few classical aspects of the analysis of this polynomial. The reproducing kernel of polynomials of degree less than n is this Christoffel-Darboux kernel, well known in all kinds of impersonations. It has been around, as you can see, for a very long time, and is related to major advances in the construction of Kubachev formulas, in approximation of functions, and in particular in the modern theory of approximation. The asymptotics of this kernel give a lot of information about the measure. On the diagonal, this kernel is computable by a variational principle, namely the point evaluation versus the norm with respect to L2 norm with respect to that measure gives us precisely the value of this kernel on the boundary. And now the inverse of it is called the Christoffel function. Is simply again obtainable by a variational principle, and is the reciprocal of this kernel. You see the dependence on the degree, n is the degree here, and the rather simple minimization problem, optimization question which appears here. In practice, we let age of W to be 1, and then we minimize simply the norm of the L2 norm. Now, why is this good? This was recognized very early. Hamburger, in his memoirs on moment problems, used this quite effectively, and probably the first striking application for this group of listeners is the uniqueness in the moment problem on the line. Both Marcel Ries and Evan Lina remarked that the moment problem has a unique solution if and only for a point outside the real line, the limit of this kernel is 0. Now, this is a decreasing sequence. It comes from the variational principle. And this is, as you probably know, a very difficult, not accessible by simple criteria question. And this gives a clue why the measure has or doesn't possess unique, is determined by the moment. We denote simply by lambda the limit of this monotonic sequence. And also interesting, if we now look at points on the line, it was well understood, starting with Stiltjes even before Hamburger, that the value is attained, and in fact we have equality here between the charge, the weight of the measure, how much mass this measure puts on a point, and the Christoffel function. There is much more. I turn the page for those who are fond of function theory in the disk. Seger's theorem is well known. What is interesting, if we have absolutely continuous measure on the circle with a weight W, the young Seger discovered that this minimization procedure gives exactly the geometric mean of the weight. And this was the beginning of a whole story in approximation theory, as you probably well know. You all know. And just to show you that the optimization problem we discussed gives you precisely the geometric mean of the measure. Now, if you put this at work and you look at the Lebesgue decomposition, we go in that direction of a measure on the circle. Kolmogorov and then Crane discovered that you have a completeness of complex polynomials on LP spaces. Let's say on L2, we spoke about L2 before, if and only if this Seger condition is satisfied. So this is, again, just to show you the strength, the big weight this rather innocent looking function, the Christoffel function, carries. And just to finish this part, for instance, we are looking at the Fourier series with respect to orthogonal polynomials associated to measure alpha on the line. Just simple manipulations of the Fourier series, so the L2, the Cauchy inequality here will give us that the partial sum has precisely this bound. Alpha is the mass. And therefore, Lebesgue was the first to realize that the gap between the function and the partial sum can be estimated as follows. We add and subtract polynomial. For polynomials, this is exact, of degree less than n. And we obtain here the Chebyshev constant, the best uniform approximation of f by a polynomial. And here constant which depends solely on the Christoffel function. And that is the root of a lot of improvements of the convergence of Fourier type series. So that's just to close and this review of many applications of the Christoffel function. Probably everyone in this audience has a favorite interpretation and application of it. In the unit disk, if we put a uniform mass, it's a different story. This reproducing kernel, of course, will converge to what is called the Bergman kernel of the disk, and there are estimates which are very simple and easy to obtain. And they are the root of the famous Kahneman asymptotics of the Bergman kernel via conformal mapping on domains with relatively smooth boundary. And then, of course, they were extended, especially by the Russian school, to more rough boundaries. So just to show you that inside, when we have a uniform mass, this kernel has a limit. It's finite, even on the diagonal. And no surprise, these points, when the limit is non-zero, will detect bounded point evaluations in the respective norm. And to finish, if you want to remain with a simple computation and to see the wonders of this Christopher Darboux kernel, let's take the Haar measure on the torus. The partial sums are computed, as you know, immediately. The monomials are orthogonal polynomials. And if we are looking at the value of this kernel on the diagonal, this is positive, so it's equal to its absolute value. Immediate computation will give you n, exactly the degree associated to this. So for this, how to say, extreme situation, not only that the limit is 1, but at every single degree level, the quotient is constant, is 1. And this is the beginning of the proof of the main theorem, which I mentioned at the very beginning. Now, basic references in this direction, there are many. It's a whole industry. The whole theory of orthogonal polynomials gravitates around Christoffel functions. Paul Nevai has a very beautiful and long article about the might of Christoffel function as discovered and promoted by Geza Freud. I recommend you warmly to have a peek and to see a little what you can do with this. On a more recent scale, Barry Simon turned to the Christoffel Darboux kernel from the point of view of operator theory, and he has some very beautiful accounts and advances in the 1D situation. I recommend this survey article, but he has quite a few others. And Vilmos Totic is the big master. He proved the most refined results, which were discovered little by little, starting from Seger and Freud and Nevai and quite a few others. He has the best, to my knowledge, asymptotics for the Christoffel function and applications of these asymptotics to orthogonal polynomials. So that's the very brief and sketchy picture of the 1D situation. Now, what we can do in higher dimensions? Much less, unfortunately. And here I turn to some objects of interest to this audience. So we like to separate outliers from the bulk, from the cloud, and I'll consider a compactly supported positive measure on C. And speaking about operator theory, immediately what comes to mind is the closure of polynomials in L2. We have this subnormal operator, and in this setting, there is top result, which culminates a long struggle of understanding the structure of cyclic subnormal operators due to Jim Thompson in 91. So let's take the time to analyze a little what Jim Thompson theorem says. There is this positive measure, and then the closure of polynomials in L2 is decomposed rather, I would say, geometrically, physically, into a normal part, an L2, and a direct sum of closure of polynomials into restriction of this measure to subsets, where, that's the interesting part, every summand of the subnormal operator represented as a direct sum of operators here is irreducible. The spectrum is precisely a simply connected open set. The support of the measure is in the closure. And, oh, sorry. And they are disjoint. So there is much more to say here. We have experts around, and what it is interesting, this theorem came after Scott Brown discovered that every subnormal operator has an invariant subspace, but it gives much more structure than an abstract invariant subspace theorem. So the closure of polynomials is equal to L2. That means there is no other part here, if and only if this subnormal operator is normal. And in that situation, there are no bounded point evaluations. Why? Because the difference between the spectrum and the essential spectrum here provides a large set, an open set of bounded point evaluations with respect to L2 of this, this measure. So this is very similar to the density of polynomials, complex polynomials in L2, what we discussed before, but is much deeper because it applies to every positive measure on the complex plane. So what I would like to do now, the task, and I'm getting closer to the aim of this talk, is to eliminate the normal part, but by operating only at the level of moments, and to put a uniform mass on the leaves on these open sets carrying point evaluations. Of course, the measure there may have no mass, can only encircle these points, but what it is interesting for us and close to the aim of statisticians is to compute only at the level of moments the shape of what we call the cloud. And now, to this aim, I use operator theory, namely hypernormal operators. I'll not go into full details here, but just to give you a definition, how do we separate the normal part from the subnormal part? Obviously, we take commutators between the operator and its adjoint. And when doing so, the normal part will disappear. Normal operator has, of course, from definition, the property that the commutator between the operator and its adjoint is 0. So if we do commutators, and here we take arbitrary polynomials in any order, some deep results of hypernormal operator theory lead to the following trace formula. There is a Borel set which carries uniform mass with respect to Lebesgue measure. dA is the area measure. So that the trace of the commutator of these two polynomials is precisely the integral of the Jacobian of these two polynomials. Now, this cloud is precisely modulo null sets the union of the leaves of the open sets in Thompson theorem. And therefore, our task is now to put this formula at work. This is called well-known Helton-Howe trace formula. Here we have the principal function due to Pincus, but we need a little more. And I'll skip the details. Rather, I would like to show you some interesting examples. So again, I'll go back. We have this decomposition. I want to get rid of the normal part and put uniform mass on the sets which carry bounded point evaluations in this decomposition. Here you can see another plot. So what I want to eliminate, typically you have point masses and you have a bulk. And I want to eliminate these point masses and to put just a dark picture mass here on the cloud. So we are back to orthogonal polynomials, a little more structure. They correspond, of course, to powers of the subnormal operator on the cyclic vector. And the matrix associated to the multiplier in the basis of orthogonal polynomials has a name. It's called the Heisenberg matrix, and will play a role in our computations. So this is a matrix which has only one subdiagonal. Think of the unilateral sheaf, for instance. And the main result is the following. Start with a positive Borel measure. Suppose that we have access to the moments. Compute the orthogonal polynomials, hence the Christoffel-Darboux kernels. And take an arbitrary polynomial here in Z and Z bar. I would like to compute the moments of the cloud. Well, using the trace formula, it turns out that this is precisely a double limit, which involves only the Christoffel-Darboux kernel and the original integrand. Now, this is interesting because when we take such products, suppose that we have the decomposition, again, here we have only the moments of the measure up to the respective degrees. Now, questions of convergence arise, and questions of the asymptotics and the degree of the convergence of this formula holds. And here is the estimate. The error depends only on the Heisenberg matrix. And you can see it's quite involved, but in particular situations, you can have finite bounded matrices, and then it's rather effective. And it gives you a hint where to look for the degree of convergence. Now, for the operator theorist, I didn't put all the details here. Behind this is the Hilbert-Schmidt norm of a Hankel operator, which is related to the self-commutator of the subnormal operator. And that's essentially the main character behind this formula. Now, stability, it's first question, how stable this scheme is. And it turns out that if we perturb the Heisenberg matrix with trace class operator, nothing will happen. Even if we have Hilbert-Schmidt operator, which still keeps the self-commutator trace class, nothing will happen. This is due to an observation of Dan Voiculescu related to the stability of Pincus principal function under such perturbation. So there is some stability. Now, what happens for statisticians? The main question, if you add, let's say, 1 point mass to the bulk, and then the error will be estimated by rather rapid decay. It's a geometric decay here. So this is good news, that if you add points outside the polynomial hull of the support, so that's rather typical in approximation theory, then you have such a decay. And now I'll show you a few examples for the rest of the time. So let's consider toy example, something which we can visualize and compute by hand. So the cloud will be the unit disk, and the outliers will be distributed on 2 circles of larger radius. So you can imagine it. I didn't put here a plot. On polar coordinates, we don't have to have a uniform mass on the disk, but it's rather this rotationally invariant beta distribution. We have the moments. And on these 2 radii, we put, let's say, a continuous distribution, but only on an arc, which disconnects. It does not disconnect the full plane. So this is simply an arc. And some point masses. So this is a 1D measure on an arc. And here are some point masses even outside. We have all the moments. So you can see we have many parameters here which are reflected in the moments. You can see here. So there are 6 parameters entering into these moments. It's quite frightening. But if we run the algorithm, and we tested this numerically, is quite fast. I jump over this part. We end up, so doing this computation and limiting of the trace of commutators, we end up with a result with moments of the cloud, which do not depend on all 6 parameters. So this is quite magic. It shows that this process indeed eliminates all variations and all discrepancies in the mass distribution and gives you a totally flat picture. Now, if you have a uniform mass, there is plenty of information. We have the Bergman kernel of the respective domain. And what is interesting here, the Hankel operator I mentioned is represented by a nice looking kernel. So here is the Bergman kernel times z bar minus w bar. So we alter a little the analyticity, anti-analyticity here. And the singular numbers here are known, at least for smooth boundaries. And the error in the process of approximating the cloud in this situation is unfortunately only of the order of 1 over n. And this is rather typical for uniform mass. The ellipse can be computed by hand and gives a nice interpretation of the Heisenberg matrix. You see it here precisely. And in this situation, we show that the estimate before is sharp. So you cannot do better than 1 over n in this case. Now, the interesting part is that there are recent results about the asymptotics of Heisenberg matrices of measures in the complex plane, and they fit very well with this scheme. Finite rank self-commutator, for those who know, this goes back to John McCarthy, Li-Ming Yang, it's also of high interest, and here the cloud will be what we call a quadrature domain. I don't go into these details, and interestingly enough, in this situation, which is non-generic, the rate of convergence is geometric. There are pathologies you can imagine, and there is a whole century of discoveries of bounded point evaluations and all kinds of measures. Here is only one. Take a Jordan curve, which has a boundary with positive area measure. Believe it or not, such an object exists. And in this situation, Kahleman showed in general that for Jordan domain, the closure of polynomials is the Bergman space. And then the cloud will be slightly bigger than the interior. So the area of the cloud minus the interior minus this open set is positive, although the measure doesn't put mass there. So that's pathology. And now to finish, a few references. There is a lot to say about Thompson Theorem. It was a breakthrough, well exposed into the book of John Conway. A simplified proof is by John Brennan, who worked lifelong on bounded point evaluations. Here is the Russian spelling of his name. Two notes which I wrote specifically related to this application of hypernormal operators combined with Thompson result are here. So one of them just appeared and the other is in print. For the bigger picture of the applications of Christopher Darboux kernel to detection of outliers in mass distributions. There are two articles in the same issue of this journal, Foundations of Computational Mathematics. One is more theoretical and the other is more statistically oriented, but it's not very much connected to what I mentioned today. And to finish, I advertise a coming book, which is aimed at non-experts, with a lot of information about Christopher Darboux kernel, even in more than 2 variables, where pluripotential theory plays a big role. So this is a kind of compendium without complete proofs, but with guide of and a lot of numerical experiments showing the possibly important applications of the Christoffel function, in particular to data analysis. Thank you very much.
Thank you very much, Mihai, for a fascinating discussion here of these. The one thing that naturally comes to mind, I guess, for me as a question is whether there was about three-dimensional or higher dimensional analogs of this. I know it's somehow tied, the 2D things are tied to the fact that you're working over there's a nice connection with complex analysis. But I was wondering if there is a way of
Yes, there is. You have to put in the context of several complex variables. And there is a whole group of researchers in Sweden at Göteborg working on this. It's pluripotential theory, and there are fine results, but you have to assume from the beginning something about the measure, that it has an absolute continuous part. So you cannot expect to have the Lebesgue decomposition in a flash. But there is, yes.